The choice that echoed backwards, delayed choice. John Wheeler didn't start with hardware. He started with a question. What if you decide how to measure a photon after it's already past the point where that decision should matter? In his thought experiment, a single photon travels through an interferometer, two possible paths that can create an interference pattern if both paths remain indistinguishable. But there's a catch. You can insert or remove the final beam splitter late, so late it feels like the photon should have already chosen a path. The result. The pattern you see depends on a choice made at the last moment. That decision looks like it reaches backward. Now move from chalkboard to lab bench. Modern versions use fast optical switches and random number generators that decide, after the photon is inside, whether the interferometer is closed, paths recombine, allowing interference or open, paths separated, revealing particle-like which path behavior. When the interferometer is closed, you get the smooth interference fringes that say the photon behaved like a wave, exploring both paths. When it's open, the fringes vanish and detections pile up in a way that says the photon took a path. The weird part is timing. The setting is chosen so late it looks like the future choice dictates the earlier behavior. Here's why this moment matters. Everyday logic says causes come first and effects follow. You flip the switch, then the light turns on. If the light pattern responds to a switch flipped after the photon's critical moment, causality feels shaky. For real people in the lab, this isn't a word game. It's their equipment returning data that doesn't fit the story of tiny billiard balls tracing tiny lines through space. If that story fails our sense of I act, then the world response starts to wobble. What actually happened is painfully precise. A photon source fires. The photon hits the first beam splitter, putting its path into a sewer position. It travels down both arms, phases accrue, and then, just before it would recombine, an ultra-fast device, sometimes driven by a quantum random number generator, decides whether to insert the second beam splitter. If inserted, the two paths recombine, and the phase difference decides which detector clicks. If removed, there's no recombination. The detectors reveal which path. The experimenters verify space-like separation or tight timing, so the choice cannot be known, in time, by the photon's earlier segment. The immediate impact, outcomes match the late choice. Close the interferometer, you recover interference. Open it, you don't. What didn't happen, recombination or path marking, still matters to the statistics. It's as if the world only commits to wave-like or particle-like when you pose the question, even if the question is asked after the photon passed the fork. That's the glitch. The meaning of before and after isn't doing the work we thought. In labs and hallways, the arguments get sharp but focused. One camp says retrocausality might be on the table. Maybe future measurement settings correlate with earlier outcomes in a way that looks like influence backward in time. Another camp, the no trajectories crowd, says the mistake is assuming the photon had a single path story waiting to be read. In standard quantum mechanics, there aren't definite paths until you force that description with a measurement that makes them definite. No need for signals to the past. Just don't assign a narrative the math doesn't support. And the guardrails matter. Nobody in these labs claims you can send a message to your former self. The correlations don't let you encode information into the past. You can't pick settings to force a retroactive sentence of Morse code into yesterday. When you look only at the early detections, before sorting by the later choice, they don't spell anything. The strange behavior only shows up when you compare joint data, detection outcomes paired with the late settings. The past doesn't change. The story you can consistently tell about it does. Meanwhile, something else is happening in parallel across different groups. Delayed choice quantum erasers add a further twist. They tag which path information with entanglement, then later erase or reveal that information. If which path information is made unknowable, interference patterns reappear in the sorted data. If which path information is retained, interference vanishes. Again, the crucial piece is that the decision to erase can happen after the photon hit the screen. It's the availability of information in the joint correlations that decides the pattern. not a fixed tape of history. Here's the turning point. The delayed choice experiments don't only tease us with paradox, they force a cleaner language. The photon doesn't carry a little diary of its journey, asking which path did it really take. When the setup was tuned to produce interference is like asking which note a chord really is. The answer depends on what you measure. The late choice doesn't reach back to flip a switch in yesterday's hardware. It decides which properties become part of the record you can build without contradictions. In the aftermath, something essential changes for the people involved. Students walk in thinking physics is about tiny objects with tiny tracks. They walk out knowing physics is about correlations between preparations and measurements. One detail proves crucial later. The order of events you assumed would explain everything doesn't rescue you here. You can try to shuffle before and after, but the predictions don't care. And that's our bridge. While delayed choice bent time locally, a deeper fracture lived in entanglement, where two particles act as one system and time ordering stops being a helpful excuse. Entanglement's no-time contract. While that was twisting minds in one lab, across town, another team was doing something even stranger, splitting a pair of photons so they were born entangled, then sending them in opposite directions at high speed. Each side gets a polarizer with a setting chosen on the fly, sometimes by a fast random number generator, sometimes by light from distant stars. When they compare notes later, the numbers refuse to fit any story built from local properties and fixed time order. The data say the pair behaved like one system, no matter the miles between them. Here's why this moment matters. If two detectors separated by city blocks show correlations that defy any mix and match of pre-agreed instructions, then our everyday picture cracks. We want to say a measured first, then B responded, or B first, then a responded. But relativity lets different observers disagree on who was first. If the correlations are real and robust, and they are, then before and after can't explain the link. The stakes are personal. Researchers had to decide which part of their intuition to let go. What actually happened is a sequence perfected over decades. Early Bell tests had loopholes. Maybe the detectors weren't efficient enough, or the settings weren't truly independent. Teams closed them, one by one. Elaine Aspect's experiments in the 1980s switched settings fast so no signal could sneak between the stations in time. Later, groups in Delft and Vienna boosted detection efficiency so missing events couldn't bias the sample. Then came satellite links, pushing entanglement over hundreds or even thousands of kilometers. And then a bold flourish. Cosmic Bell tests that used photons from distant quasars to pick the measurement settings, pushing any would-be conspiracy back billions of years. The impact was unmistakable. The correlations violated Bell inequalities, mathematical limits any local realistic theory must obey. The world doesn't fit a model where each particle carries hidden instructions that say, if measured this way, return that result, all without influence from the other side. Try to fix it by saying, fine, A happened first, and relativity shrugs. Some observer sees B first. Flip to B caused A, and another observer disagrees. The pattern stays put, while time order slides underneath it. Here's the key insight that sank in slowly. Before and after aren't the levers that make the data work. The joint outcomes arise from the entangled state and the pair of settings together. If you only look at A's results without B, they look random. Same for B alone. Put them together with the chosen settings and the structure appears. It isn't a message sent faster than light. It's a constraint woven into how the joint system responds to the pair of questions. Walk the hallways and you hear the debates in plain words. Some argued realism had to go no definite values before measurement. Others wanted to keep realism but give up locality or give up the independence of settings. Anton Zeilinger leaned into the experiments, trust what the data say and refine the questions. Meanwhile, theorists sharpened the logic. You can hold on to causal order as a comfort blanket, but the correlations don't need it. Put A first, put B first, alternate them. Same predictions, same violations. We need guardrails, so let's set them clearly. You can't use entanglement to send a signal faster than light. The no-signaling theorem isn't a suggestion, it's baked into the formalism and the data. A alone sees noise. B alone sees noise. Only after the fact, when they compare, does the pattern click into place. So no, you can't warn a friend across the ocean instantly, and you can't rescue your past self from a bad decision. The correlations are strong and stubborn, but they don't carry usable messages. Meanwhile, something else was happening in new experiments that tested timing assumptions directly. Researchers engineered space-like separation so that, according to relativity, neither station could be in the other's past light cone when the settings were chosen and the outcomes recorded. They even randomized the settings with cosmic light to weaken the freedom of choice loophole. Each step tightened the vice around classical explanations. The correlation stayed, calm and immovable, as if time order were just background scenery. This was the moment everything changed for many working physicists. Entanglement wasn't a quirk, it was the operating system. Pairs, sometimes triplets and clusters, behaved as single wholes, and the language of separate parts responding in sequence felt clumsy. You could try to force a story where one side influences the other in time, but you'd be choosing a frame that another observer would deny. The better language was simpler. The outcomes are jointly constrained. In the aftermath, the field pivoted from "is entanglement real?" to "what can it do?" Quantum cryptography, teleportation, and distributed sensing all grew from taking the correlation seriously. But the philosophical bruise lingered. If time order doesn't help, what is the order that matters? That question led a few brave teams to a radical test. Set up processes where there isn't a single definite A then B or B then A at all. Let the order itself go quantum. If entanglement showed that distance can fade, maybe sequence can melt too. And when they tried it, the results hinted that before and after might not be fundamental. When order melts, quantum switch and indefinite causality. While that was happening in entanglement labs, a smaller group tried something bolder. Stop assuming there's a single order to events at all. Here, S the stakes. If the order of operations can be indefinite, A before B and B before A at the same time, then time can't be a global stage. It becomes context. And if order itself goes quantum, our old crutch for causality falls away. What actually happens starts with a clever device called the quantum switch. Take two operations, call them A and B. Think of them as black boxes that transform a photon's polarization. Classically, you'd pick an order. The photon goes through A, then B or B, then A in the quantum switch. You put the control of the order into a superposition. A separate control qubit determines whether the target photon experiences a right arrow B or B right arrow A, and that control qubit isn't set 2 or 1. It's in both. The result is a process where the target system undergoes A before B and B before A, coherently superposed, so long as the control remains coherent. Researchers realized they needed new language to describe this, because standard quantum circuits assume a fixed temporal order. Enter process matrices, a framework that lets you talk about correlations between operations without presuming there's a single, underlying sequence. Within that framework, some processes are causally separable. You can explain them as a mixture of definite orders, and others are causally non-separable. No mixture of a right arrow B and B right arrow A reproduces the statistics. The quantum switch lives in that second category. Teams built photonic versions using interferometers. In one arm, the photon sees A then B. In the other arm, it sees B then A. Interference between the arms certifies the superposition of orders. The immediate impact wasn't just conceptual fireworks. There were practical payoffs. Certain information processing tasks get easier when you don't lock the sequence. For example, distinguishing whether two unknown operations commute or not. Classically, you need to test both orders. With an indefinite order, you can do it in a single shot with higher success probability, because the device explores both sequences at once and the interference encodes the answer. People called it a causality glitch, that helps you compute. And you should have seen the human reactions. Some were stunned that causality could be a resource. Others were cautious. Is this just a trick of labeling? Experiments pushed back on the skepticism. They measured causal witnesses, observables designed to detect causal non-separability the way entanglement witnesses detect entanglement. When the witness goes negative, no classical mixture of orders can explain the data. Multiple groups saw those signatures, with better stability and tighter error bars each year. Guardrails matter here too. No, this isn't time travel. The lab doesn't let you send your future self a note. The device doesn't produce contradictions or grandfather paradoxes. What it shows is that, for some quantum processes, nature doesn't assign a single, global what happened first that everyone can agree on, even in principle. The order is entangled with the control system, and until you measure that control, before and after are not settled facts. Meanwhile, something else was happening in theory that sharpened the stakes. If you allow indefinite order, you need to rethink what causal relations mean. Without a fixed sequence, we stop defining cause as earlier influences later. Instead, we define it in terms of constraints among operations, which interventions can change which statistics. That's a different backbone for causality, one that doesn't rely on a universal time parameter. It fits suspiciously well with what we saw in entanglement and delayed choice. The data care about relations, not about a master clock. Here's where it gets useful fast. Communication complexity tasks, where two parties try to compute a function with minimal communication, can get a boost with indefinite order. Query problems, channel discrimination, even certain metrology protocols all show advantages when the lab can superpose sequences. The glitch isn't just philosophical, it's operational. Researchers learned to protect the control qubit's coherence long enough to extract those gains, an engineering challenge that turned metaphysics into hardware. One micro-story sticks. A young postdoc watched the interference fringe from the switch drift across a screen at 3 a.m., then hold steady as the causal witness dipped into the non-separable region. He didn't cheer. He just muttered, "So it's real," and wrote the time in his notebook, then scratched out time and wrote readout. But there was one problem. If order is indefinite, what anchors change? What makes events more than floating relations on a blackboard? The experiments tell us sequence can melt locally, yet our lives feel ordered. Meetings start, coffee cools, signals arrive. To understand why that feeling persists even when microorder flickers, we need a bigger frame. While that was happening in the photonics lab, relativity was waiting with a harder truth. There is no universal now to anchor any of this. Enter the block. The block universe you can't escape. 3 days earlier on a train platform, 2 clocks ticked in perfect sync until the train moved. One passenger said 2 distant lightning strikes were simultaneous. A person on the platform said they were. Both were right. That simple disagreement, who's first, who's second, wasn't a nitpick. It was Einstein's quiet demolition of a universal now. If simultaneity depends on motion, then there's no single slice of the present that everyone can share. Here's why that matters for us. We like to think time is a river that sweeps everything forward. Relativity replaces the river with geometry. Events are points in a 4-dimensional spacetime. Your life is a path, a world line weaving through that geometry. Clocks don't measure a global tick. They measure the length of their own paths, proper time, like measuring a route on a map. 2 people can disagree about lengths of segments and angles, but the geometry keeps them honest. There's no master metronome in the background, just paths and intervals. What actually happens on the ground is almost mundane. GPS satellites carry atomic clocks. They orbit fast and high, so relative to us, their time flows differently. Engineers correct for special relativity, motion slows clocks, and general relativity, gravity speeds them up higher up. The numbers match the equations and your phone finds your location. No drama, just a daily admission that time is geometry, not flow. If there were a universal now, we wouldn't need frame-dependent corrections. The system would just agree. It doesn't. Now remember, this is relativity's tough love. Carve spacetime into now slices however you like. The physics doesn't prefer one slicing over another. Some choices make calculations easier, but none are sacred. In that picture, past, present, and future all exist as parts of the block, like different frames of a film that already sits on the reel.